Hi, everybody. This is Mr. Folly, and welcome to 9.1. Yeah, we're back at it. We're going to talk about collision theory, which is a key thing to explain all kinds of reactions, and then a simple process of getting rates from tables, which is math that you've seen before, but a new application for it. So let's get started. Kinetics, the collision theory. In order for a chemical reaction to take place, particles must collide with enough energy and the correct orientation. So we know the collision theory has three parts, and this is what you'll remember pretty well, but you'll have to say why. In order for a chemical reaction to take place, particles have to collide with enough energy and the right orientation. So if I do A plus B yields C, no kidding, Charlie, A and B have to hit each other to make, instead of C, let's make it AB. They have to hit each other to make AB, right? So if it's got to be AB in that order, they have to collide with enough energy, so they've got to hit enough to stick, okay? Most reactions don't work. So that's an important thing to know. Most collisions, I'm going to change that. Collisions don't, instead of work, I'm going to use the word react. How about that? I bet Dr. Tyrell had 5 people high jump 5 feet today. I don't lose. So this is the idea. My reaction is high jumping 5 feet. So this is my analogy. So what I can do, the things you can do is increase your collisions, okay? So if I increase my collisions, I'm going to go find crowds of people and ask to jump. I'll go to football games, I'll go to concerts, and just have more and more people. So the number of collisions, number of people trying, will get me a higher frequency of successful collision. Now, that's not a higher rate. Still, only 1 out of 100 people can do it. But if I find 10,000 people, I'll have enough people that can high jump 5 feet. The other thing I do is increase my energy. So if I make people try harder, give them more energy, give cash prizes, give energy drinks, warm up, more energy is a higher frequency of successful collision. So I might pick strong people to high jump instead of weak people to high jump. Should make sense, right? A catalyst. A catalyst is something that speeds up a reaction but isn't used up. So if you're going to high jump 5 feet, what if I put a trampoline at the base? Oh, this way people will require less energy. Put the 5-foot high post in a hole so it's easier. So what happens with a catalyst? A catalyst reduces the energy required. Okay? So see how things must collide? Higher number of collisions for my first one. Increase my energy. More energy. Obviously, that was pretty easy. Catalyst reduces the energy required. I can increase the concentration, okay? So this is kind of where it ends with my little analogy for high jump. Jump. And it works for the other ones. And this is, oops, let's get out of here. This is chem. So I'm going to focus on the chem part now. Increasing the concentration increases the particles per volume. This gives us more collisions in the same time. So more collisions, higher frequency of successful collisions, okay? Decrease the volume of the gas. So if I make my container smaller, that increases my concentration. Let me draw a quick picture of what I mean by increasing my concentration. So if I have this box and I have 1, 2, 3, 4, 5, 6, so my particles have disappeared. So let's try it in a different spot. So if I have this box, that's this side, I have 1, 2, 3, 4, 5, 6. And what if I make the box half the size? And I have 1, 2, 3, 4, 5, 6. You see how they're going to collide more often if they're all moving at 20 miles an hour, right? So I decrease the volume, and remember, these guys are moving. The dots are moving. Boom, 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 boom. If I increase the temperature, this is a double whammy. That means you need to say both of them. So higher temperature means the particles move faster. A higher frequency of successful collisions. Remember how more energy gets you more successful. And more collisions, right? So you have more energy, bump, 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 and more collisions. A catalyst lowers the energy needed to react. So you get a higher frequency of successful collision. So that increases the successful part of it, okay? Increasing the surface area makes so there's more collisions. So a higher frequency of successful collision. So let's look at it again. If I want to say surface area, more collisions. Catalyst, lower energy. Increasing the temperature, I have more energy and more collisions. Decreasing the volume, I have, I'm going to go up here, it's going to be more collisions. Increase the concentration, more collisions. Remember, to make a reaction go faster, you either have to collide with enough energy or the correct orientation. And that orientation thing we don't see very often. I'll show a demo in class of some of the orientation things that'll work. What doesn't speed up a reaction? So sometimes these are our tricks, okay? It seems like it should, but it doesn't. If I add more solid or liquid, that does not speed up a reaction. No. You need more collisions per time. So more solid or liquid will react longer, just not faster, as the number of collisions per time is the same. If your job was to drown puppies, oh, how sad. If you do it in a 20-foot pool or a 30-foot pool, it doesn't matter. More liquid isn't a faster rate of drowning puppies. Don't drown puppies. That's terrible. But I think that might be memorable, so you can see that just the amount of liquid or solid doesn't change it. Changing volume or pressure doesn't do anything unless it's a gas. This doesn't change collisions per time unless it's a gas. Okay. The reason why that does change it for a gas is gases then would change their concentration. Remember, brackets means concentration. All right, that's part one. I'm now going to go to my smaller pen, thinner pen. Oh, come on, you can do it for me. Thinner pen. There we go. Good. Table 12.1. So tables for rates. So the concentration of a reactant and product as a function of time for this reaction. So this means I'm going to start off at time 0. And I have 0.1, nothing, nothing. And then notice as I go down here, this is minus 0.21. This is plus 0.21. And this is plus 0.11. Okay. Now, if I looked all the way down at the bottom, then this time is 50 seconds. So I could do my rate for NO2. Remember, rate is change in something over change in time. Now, I'm going to be honest with you. It's typically going to be change in molarity over change in time. So for NO2, my change is going to be 0.21 over 50. Okay. So I'm going to see if this rate changes. So from 350 to 400, that's 50, not 500. And this is going to be 0.0003. I just subtracted them, right? So this is going to be at time 2. It's going to be 0.0003. Notice how it's change in molarity over change in time over 50. Those numbers are not the same, my friends. I'll put a number to them. 0.21 divided by 50 is 0.0042. And my units would be molarity, the number on top, per second. And 0.0003 divided by 50 is, it gives me right to scientific notation, 6e-6 molarity per second. All right? So let's do just some sample problems. That's the idea behind it. We've got the change in molarity over change in time. Okay? So let's take a look, and let's do it. Do some sample problems. We'll be done. What's the rate for the first 100 seconds for no? So there's 50, there's 100. So it's going to be change in molarity over change in time, which is going to be 0.0035. Notice how from 0 to 0.0035 over 100. Dividing by 100 moves the decimal 2 spots. 0.000035 molarity per second. What about for O2? For the first 100 again. 50, 100. So it's going to be 0.0018 over 100 is 0.000018 molarity per second. And this, again, concentration is in moles per liter, which is molarity. Does the rate of the reaction change over time? Is the rate the same in the beginning, the middle, and the end? So remember in the very first part, I said in the beginning, NO2 equals, let's see if we can do it again, NO2 equals 0.0042 at the start, and NO2 equals 6e-6 in the end. So rate changes. And that's it, right? And this should make sense. Most reactions slow down. So you start off with a lot of reactants, and then you run out of reactants. Okay, so if I'm trying to eat Oreo cookies as fast as I can, Cookie Monster, cookie, 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 cookie. After a while, I tire, which would make sense that I would eat slower. Or if I had, if I'm trying to grab, we did the paperclip thing. If I'm aiming and trying to grab something, if there's fewer there, it's harder to grab it. But the good news is that is it. So to that, I will say,